Some people think climate change is in the future. I think it's already now.
Matthew S. Johnson, professor of chemistry at the University of Copenhagen.
If you're one of the people who's been displaced by this effect in the sub-Saharan Africa, climate change is now. This is a very immediate problem that you have. If you're a tech billionaire and you have your own yacht and you've made a refuge on New Zealand where you can go and live off grid, climate change is never going to affect your lifestyle. And I think the rest of us are really somewhere in between on this continuum where we are starting to see the effects in our daily lives. Changes in the supply chain for food are definitely linked with climate change. So we're all impacted by this.
When most people think about climate change, we often default to think about carbon. But why should we now be equally aggressive about methane emissions?
One, that it has 2/3 of the climate impact of carbon dioxide, even though its concentration is only 2 ppm compared to carbon dioxide at 400 ppm, right? So we have 200 times less concentration, but a very large impact. We need a good playbook. We need to understand what the effect of different things would be, what the effect of natural mineral dust is, what the effect of current human activities is, and potentially what the effect would be of trying to change those activities. Maybe we would find that we should actually reduce human emissions of iron because that would help the environment.
Bonded by Science, proudly presented by Noble Blocks.
Thank you so much, Matthew, for joining me for today. This is actually our weekend, so this is the stuff that we do for fun, right?
Oh, that's
it. Talk about science and everything that's brewing around it. Thank you so much for joining us on Bonded by Science, and welcome.
Yeah, you're welcome. Thank you very much, Shelley. Glad to be here.
So we have a lot of things to discuss. There's so much going on in your life personally, but also professionally. And the two of those, from what I understand, have a massive overlap. So I would like to dive right into a question about methane, because when you look at your research and the things that you've been involved with, methane is sort of a common denominator in a lot of those projects. So when most people think about climate change, we often default to think about carbon, because that's the narrative that's been pushed for the last, I would say, 5 years quite strongly, even though it's been in the scientific literature for 2 decades. But why should we now be equally aggressive about methane emissions?
Yeah, very interesting question, and you're exactly right. Carbon dioxide has gotten all the attention in this area. The reason we should think about methane is it's a really large opportunity. That's for a couple of reasons. One is that it has 2/3 of the climate impact of carbon dioxide. So already there, it's a very large target. It has 2/3 of the impact, even though its concentration is only 2 ppm compared to carbon dioxide at 400 ppm, right? So we have 200 times less concentration, but a very large impact. Now, the other odd thing about methane is that it stays in the atmosphere for a relatively short time. That means that if we do something, we can have an effect, an impact within the next decade. So carbon dioxide might stay in the atmosphere for centuries. With methane, it's a decade.
Okay. So when you say methane stays in the atmosphere for 10 years naturally, where does it go? What happens to it?
It gets broken down. There's radicals in the atmosphere. They break it down into carbon dioxide, actually.
Okay, so it actually is a precursor for one of the problems that is so strong in the narrative. So if we reduce, it's basically like saying if we reduce a main source of carbon, which is methane, I guess would be one main source, if you track it back to its root, then not only does it have an immediate effect, potentially over a shorter timescale relative to removing carbon, but it also mitigates the future climb of carbon, 10, 20 years from now.
Yeah, that's right. So methane is a source of carbon dioxide in the atmosphere. There are other larger sources of carbon dioxide. But, another aspect of this is that there are some serious climate tipping points that might be coming within the next few decades. And so if we want to avoid those, carbon dioxide is not a lever that you can pull quickly. Methane is. So we should pull that lever.
Yeah, that's a really good point. What are the current sources of methane now? Like, so if you were to meet someone on the street that was slightly, climate sensitive, right? So what if we were to interview those people, or maybe even some of the students that are taking some of your courses at the university, some crossover education, what sources of methane might, the average person be aware of?
Yeah. You can say methane, it's of a different character than carbon dioxide, right? Carbon dioxide, you think, burning fossil fuels, it's one simple source. But methane has a lot of sources, and I think most people would say cows.
Yeah,
Right?
that's a big one.
That's like the poster child of methane. And certainly a lot of it does come from agriculture. There's a lot of it coming from wetlands, and fossil fuel production makes a lot of methane.
How does it come from wetlands?
Yeah. Well, growing up in Minnesota, you spend a lot of time hanging around in lakes, and you walk through a bog and there's just gas bubbling up, right? And we've all seen that kind of swamp gas. And what happens is when you have organic material, dead plants, whatever biomass it might be, if it's underwater, so anoxic conditions, it can't burn up through oxidation the way that it usually does. So you get some fermentation processes, and that breaks down that carbohydrate into methane and carbon dioxide. And so that's that swamp gas is like methane and carbon dioxide. Now, that means that whenever we have organic material in anoxic conditions, it'll be a source of methane. And that could be a garbage dump, or it could be inside of a cow's stomach. Actually, termites are a very large source of methane. They're also eating a lot of cellulose like the cows do, but they make a lot of methane. But it's the same thing in wetlands and rice paddies. There you have organic material underwater, and it decays and it gives off methane.
Okay, so the rice paddies. So we eat a lot of rice globally. So they are then, would you say they're almost approaching an equivalent concern as the amount of land that we are using to graze cattle?
Oh, I don't know those numbers, but I think it certainly is a lot of land. I know that there are changes in agricultural practice that could reduce the amount of methane coming from rice paddies. So there are definitely people working on that. I think also that there's a lot of cows in the world. It's like 1 billion cows, and they have twice the biomass of people. So maybe there we could also do something to reduce the land use, because you've got to grow food for all of those cows, whether it's corn or they're grazing on grass or something. It does take a lot. It has a very large footprint.
Yes. Yeah. Also, like in creation of the feed as well, because if we really go back to the roots, because a lot of, even just to transport the feed to the cow or to grow the feed, there's a lot of equipment that is used to make that happen, and that equipment runs on fossil fuels. And I know fossil fuels also, people don't think about it as a source of methane, but I think I came across a few concepts where they say that you can have methane leaks in when you are like extracting some of the crude oil. Is that correct?
That can definitely happen. Whenever you're pumping oil, there's a lot of gas that comes out of the field at the same time. Depending on where you are and what the practices are, in some places they just vent that methane just as a waste. In some places they at least flare it, but certainly the liquid fuel is more valuable than the gas if you don't have the infrastructure to take care of it.
Right.
Now, even if you are trapping it, there are still leaks in all of that process, right? And you could have just a leak between pipes that you need to fix, or leaks out of the field. If you're flaring, a lot of the methane goes through the flame without being burned. And I've seen estimates up to 10% of the methane that just goes straight through the flame in a flare. So even there's a lot of methane coming into the atmosphere.
Yeah, and this is a constant process.
I saw some very nice satellite maps of things like the Permian Basin in Texas and Azerbaijan and other places where you can definitely see a methane hotspot whenever you have that fossil fuel production.
How do you see the hotspot? Is it like a thermograph that you're using?
Yeah, you can think of that satellite as, just making a map, but it uses a different wavelength of light. And then here it's infrared light, and that infrared light just shows methane. So it's like a heat-sensitive camera for methane, something like that.
Mm. And is that also related to why methane contributes to global warming, like that link for how we measure, but also
that's
how
really
we...
good.
Yeah, okay. Yeah.
That's exactly it.
Yeah.
It's because methane does absorb infrared light, and that's the heat energy that should escape from the Earth.
All right, so that's super interesting that the tool that we use to measure is actually the tool that is one of the concerns that many of us are worried about and that we're focusing on. And not to make this like a doomsayer podcast. I mean, I think there is a lot of like active solutions, a lot of solutions that are commercially available, and we'll get into some of that. So there's a lot of hope. As someone that transitioned from like medical science and then started to look more into what was going on in the environmental landscape, specifically related to energy and energy renewables and storage of renewable energy, I didn't feel less hopeful. I felt more hopeful that there's a lot of scientists and a lot of entrepreneurs that have been working like round the clock for the last 2 decades on trying to produce sustainable solutions for us to move forward in a healthier environment. And I think this actually brings me round to one of your most recent publications, which seems to be like it could maybe has the potential to be a landmark publication. I don't know because I'm not an expert in this field, but it definitely is something that would raise some eyebrows. And one of your recent publications, it seems like you found an explanation for unaccounted methane production in the atmosphere. Is that a correct interpretation of, or at least you found evidence that would explain some of the unaccounted methane?
Yeah, that's a very interesting observation and something that we didn't expect when we started doing the research. So what we found was that when you have mineral dust in the marine boundary layer, those minerals combine with sea spray aerosol. And of course...
Like, what is aerosol? Like, when you say sea spray aerosol, is it just like the waves hitting and then the water going into the air? Just really, really simple stuff.
Yeah, that's it. Well, you can think that a wave crashes, it forces water under the surface of the water, right? And then that air comes back up towards the surface. And then you get the bubble is going to break and it creates a membrane of water at the very surface. It gets thinner and thinner, and at some point it shatters. And then you have the pressure of the air behind it, and that blows these particles into the atmosphere. Some of that water evaporates, and then it leaves behind a kernel of the salt water and the organics that are in the ocean. And then everybody is, or maybe not Midwesterners like myself, but a lot of people have looked out over the ocean, and you just see this haze, and it looks kind of nice, and the sun sets through that haze.
Just with your with the naked eye, you see the haze. Okay.
Yep. That's aerosol. That's these particles. They scatter light. You might have heard of aerosols that cool the climate, and they do that because they're scattering visible light from the sun.
Right. So it's not concentrated.
But the sea is generating these, so they're all over the planet, and it naturally cools the planet. It helps with the formation of clouds in the atmosphere, so it changes meteorology. But in this case, that sodium chloride is a source of chlorine atoms. And what happens is that the iron is released from the minerals. It combines with the chloride and the sodium chloride, and that makes an iron chloride that's able to absorb sunlight. And when it does that, there's an electron transfer reaction from the chloride over to the iron atom. That releases a chlorine molecule. This generates chlorine atoms that react with methane. So that's the foundation of this effect.
Just so I'm clear, where does the sodium chloride coming? Where is that source? That's coming from the aerosols?
That's sea salt. That's all it is sea salt.
That's the sea salt. Okay. So yeah, your table salt, right? So
Yeah,
when you think about that. So okay, salt coming from the water goes into the air. It hits iron, and when it's sunny, you basically, that catalyzes the reaction when the sun is present. Is that right?
That's it. That's like the first part of the story. Now, the second part is, what do we really know about the sources of methane to the atmosphere? Because you could add up all the cows and all the termites and all the rice paddies, and you'd only have part of the budget, and you'd have errors in that approximation. And the problem is, methane is made by microbes, and it's hard to integrate over all of them globally and come up with an accurate number. So that's what they call a bottom-up estimate, where you just make an account and you list all of the individual sources. Now, there's an alternative approach, and that's what they call a top-down budget estimate. And here you get a sample of methane from the atmosphere. It has certain stable isotopes in that methane. There's some 13 carbon, there's some deuterium, and then that abundance of the stable isotope should reflect the different sources of methane. And like biological methane is very depleted in 13 carbon. Fossil fuel methane is only slightly depleted in 13 carbon. And then you can just add those up, and you should get the atmospheric composition. So if you really want to do it right, you need to make an adjustment for the mechanism that washes methane out of the atmosphere. And that's radical reactions in the atmosphere. And there's something called a kinetic isotope effect. So some of the isotopes react faster, some of them react slower. And, normally the hydroxyl radical removes methane. It has a slight effect on the abundance of 13 carbon. But if the methane reacts with a chlorine atom, there's a very large effect. There's a very large effect on the 13 carbon abundance. So we discovered this new source of chlorine to the atmosphere, this effect with mineral dust and ocean sea salt and making chlorine atoms. This increases the amount of chlorine in the atmosphere, the amount that we know about. That means we need to go back and revise our estimate for the top-down budget of methane and the emission sources. It means we've been under-evaluating the role of biological sources. There's other research, for example, Ewan Nisbet, who has been saying that there's increased release of methane from things like tropical wetlands. And this could be a climate change-related feedback, because these wetlands are warmer and there's more rainfall in these tropical areas. So he believes that, there's more methane coming from wetlands due to a climate change feedback. And then our research is pointing in the same direction. We're saying that there is room in the budget for that revision in order to show that more methane is from these biological sources and maybe a bit less from the fossil fuel related sources.
Right. And just to clarify here, because people will hear wetlands and they might think, oh, but that's a natural source. But you're saying, well, yes, it's a natural source, but it's being facilitated now because of human contributions to climate change.
Yeah. That's exactly right. And that's a large worry. And there are other effects like that. And one of them could be melting permafrost or Arctic lakes that start to warm up, and you have more production of methane. And so, how much methane is that? Do we really need to be worried about that, unlocking these other sources of methane? And the answer is yes. It's a very significant amount of methane relative to what's already in the atmosphere. So when I say that, we need to do something about methane in order to prevent these climate tipping points, that's the perfect example of a tipping point we would like to avoid, where climate change is kind of going out of control with this positive feedback that's making more climate active gases.
Yeah, it's a really vicious circle, sounds like. But the knowledge that we have now, as you pointed out earlier, is that we have some levers for methane. Like if we focus on methane, it is a strong lever. So this vicious circle doesn't have to continue, provided that we acknowledge the role that methane is having, but also acknowledge the potential other sources that are producing methane. Because as you said, the budget didn't add up. So that's basically like what's coming out and what's getting depleted, and what you measure in the air doesn't account for all the sources of budget that we can think of currently. So this is a very comprehensive understanding of where methane is coming from, but I'm curious, what was the cookie crumbs that got you there? Because no one just says, hey, the budget's, if you look at a financial budget and you see you're losing money somewhere, you're going to go look to see if you're paying a subscription for something that you forgot that you had, right? So was it simply because the budget didn't add up and that intrigued you, or how did you know to look?
There were some things that didn't add up.
Yeah, that was the main driver.
That's exactly right. And we really came at it from two independent angles. So one of these pieces of evidence was there was an atmospheric researcher. His name is John Mack. He was obtaining samples of air on Barbados in the late 1990s, just taking flask samples of air. He would then take them to the laboratory. They had a isotope ratio mass spectrometer, and was just analyzing the abundance of 13 carbon in the carbon monoxide in that air. And there's a natural cycle due to, carbon monoxide is made by biomass burning, and it's made by breakdown of methane and other gases in the atmosphere. So it naturally goes up and down in an annual cycle. And he was seeing very large depletions in 13 carbon, and actually the largest depletions that have ever been found anywhere. So, definitely a strong effect. It was reproducible over several years. It seemed to be local because it wasn't being seen at other places where they were doing similar analysis. So it was also episodic, where there would be spikes of these 13 carbon depletions, but then it would go away. So at the time, this is 20 years ago, they wrote the paper. He said, this could be evidence of a new source of chlorine atoms, but we don't know what that source is, and it's outside of the scope of currently known chemistry. And that was it. And then that paper got some references, as academics do, but people didn't think a lot more about it. Now, that's one of these lines. And then the other, completely independent line of research is that there was an inventor in Germany who was thinking about possible climate interventions. And he was thinking that you might be able to use iron chlorides in a catalytic fashion as an intervention. So, we discussed earlier that we found that there's a natural effect where mineral dust could form chlorine atoms. But his earlier work was suggesting that this could be used as a form of geoengineering, where you could intentionally add iron to the atmosphere. It would be catalytic in iron because after the iron forms the chlorine atoms, it reforms this iron chloride. It could also be catalytic in chlorine because when chlorine reacts with methane, you get hydrochloric acid that will go back into these particles. So it would be catalytic in two ways. And that catalytic efficiency could potentially be high enough that, a small amount of iron could have a very large effect on climate. And that would make it scalable. So that would be very important. So we put those two things together and we thought, maybe it's already occurring naturally. And, and that I think was big news. And the journal and the editors agreed with us. Seemed to be a very large story. We're very excited about that research. One of the things we're working on right now is to say that, maybe, it's a natural effect, but maybe human activity is already stimulating this kind of chemistry. And that's because human activity makes iron. Maybe you've got an iron foundry or some mining activities, or iron can be found in shipping fuel. And so maybe in the plumes along shipping lanes, you would have this kind of iron chloride chemistry.
Okay, so just if we just go back a bit, so you talked about like putting iron into the atmosphere as a form of geoengineering, and that can sound a little scary for people that maybe are less familiar with how things are working and the potential unexpected uncertainty, the unexpected effects and the uncertainties that could, what we don't know, what we don't know.
My short answer to that is that we have a very good governance system on this planet where there's things like the International Maritime Organization and the Environmental Protection Agency. And there are international treaties that govern what is and is not allowed. And I place a great deal of faith in environmental lawyers and that kind of governance system and our democratic institutions to look after these things. So I'm a researcher. The governance side of it is not my business because I'm not a professional at it. I'm a voter. That's about the level of my participation in it. But I think that we need a good playbook. We need to understand what the effect of different things would be, what the effect of natural mineral dust is, what the effect of current human activities is, and potentially what the effect would be of trying to change or enhance those activities. Not enhance, but maybe we would find that we should actually reduce human emissions of iron because that would help the environment, right? I'm kind of an agnostic about what the outcome of the research would be. I need to be. I'm not an advocate for anything. I'm a researcher.
Right. In some of the papers that you mentioned the Sub-Sahara, and I was like, what? Like, how did this get into play? And is this the source of the minerals, or one main source of the minerals that are coming across, like that are contributing to that haze that we're seeing? Or was that also part of the breadcrumb trail?
Yeah, it's a fascinating effect. It's a very large effect. It's something that I had to learn about. But there is a lot of dust coming off the Sahara Desert. That desert is getting larger, so the amount of dust coming into the atmosphere has increased.
Why is it getting larger?
The deserts are growing, and there has been a drought in that sub-Saharan region of Africa. It's resulted in a lot of refugees, and we hear of wars that are going on due to lack of food and other pressures. But some people are saying that this is an impact of climate change, that the desert is growing and you can't grow food where you used to lead to food. For example, the Department of Defense says climate change is a threat multiplier, and it's resulting in conflicts across the globe. So the narrow view is it's made more dust. Yeah.
Right. And that dust is contributing to, one of the methane issues that we're...
It's a global...
And it could grow.
Yeah.
I think a lot of people have an understanding of, it's very hard to imagine, what you'll be like personally in 20 years. It's probably even harder to imagine what the world will be like in 20 years. We've all seen like post-apocalyptic movies. So there is like some, hints of potentially what could happen. But I think what you mentioned about like a lot of the refugees that in the growing, deserts in certain parts of of the world, they're not on our doorstep. But I can say that we get sand, like we get the sand coming up all the way up to Denmark, which is where I'm sitting currently. And
Yep.
well, you're not that far away from me, so so
We
you're
get
pretty
it to
close.
southern Sweden.
You're sitting in Sweden right now, is that correct? Yeah.
Yep.
So I mean, we get the sand up here. So this is actually on our doorstep. So even if people think, well, they feel remote to the problem, and that remoteness makes it hard to trigger our I don't want to say our fears, but it makes it hard to trigger action, because that's just, I think, comes down to our biology, and our brains are built to understand, well, probably 30-40 year lifespans, rather than 120 years lifespan. So we're just like, we're not built that way. But fortunately, we're very adaptable. Our brains learn stuff all the time, and we are now enhancing our lives in other ways. So it is on our doorstep, is what, like, that is the take home. The wind is gonna blow, and as the deserts get larger, and potentially as climate change affects other aspects of our weather, we may actually see stronger gusts of wind occurring as well.
Yep. Yeah. Increased drought, increased rainfall, all of these things. Yeah.
And then there's also the refugees, and then there's the other aspects of that displacement.
I think they say that the only constant is change, and so
well, change is good. It can be good. Things that don't change are dead.
I think it's interesting how some people think climate change is in the future. I think it's already now, but it depends a bit on what your perspective is. So if you're one of the people who's been displaced by this effect in the sub-Saharan Africa, climate change is now. This is a very immediate problem that you have. If you're, a tech billionaire and you have your own yacht and you've made a refuge on New Zealand where you can go and live off grid, climate change is never going to affect your lifestyle. And I think the rest of us are really somewhere in between on this continuum where we are starting to see the effects in our daily lives. It could be that we're involved in storms, and it's something I think everybody on the planet has noticed. Changes in the supply chain for food are definitely linked with climate change. So we're all impacted by this.
Yeah, it's on the doorstep now. It's getting very, very close. And as you said, for some, they're living it, and others, they're sort of hiding out potentially from climate change.
Yeah. But the other thing with change is it is a constant. Things have always been changing. I'm seeing the human response to this also changing very rapidly, and I think this is an area where entrepreneurship can really help us move forward in a good way. And I think 20 years ago, we would never have predicted the growth in renewable energy sources that we've seen. And even the decarbonization of the energy supply, simply the shift from coal to natural gas, has significantly decreased carbon dioxide emissions. And that's ongoing, where we want to go from natural gas even towards batteries and hydrogen as the energy carrier.
Right. And one of the approaches to, of course, decarbonize those processes are also like improving how things are harvested. What happens to all the byproducts that are produced during that as well. So that the oil and gas industry has a huge role to play. And they also have to undergo a lot of change, like probably faster than the other industries if they're really going to contribute to this success. But I'm aware that you have also been working on not just one, but like several types of technologies that are addressing some of the climate issues, specifically around how to work with methane. And one of the more recent ones that you're working with in ambient carbon, you have a role to play. So you know a lot about this because, number one, you're a university professor that teaches chemistry. And number two, you're when you say you're just a researcher, I would argue that you are actually on the cusp of two things, right? So you're also an entrepreneur yourself, and you've taken your research out and you have developed and pushed for ways to commercialize that, to make it available to address these solutions. And while you're not a politician, because I think that was your point, you're not a politician, you're not going to be the one that goes and lobbies for change, but you will provide evidence to support those that will lobby for change. So you are also an entrepreneur. Will you tell me a little bit about ambient carbon, specifically as it relates to the research that you just shared with us?
Yeah, very happy to do that. And it's also an interesting question about, why do we do what we do and how we see ourselves in the world. But we can save that part of it for later, because ambient carbon is very exciting. I'm very happy about this. So it is based on research we did at the University of Copenhagen. So it's a process that I discovered with a master's degree student, Sylvia Puglisi, and a postdoc, Johan Schmidt. And so we were working together. Actually, we were talking with the ice core people at the University of Copenhagen. And they analyzed the gas coming out of ice cores, and they wanted to analyze for laughing gas. And they found that the methane present in the gas was causing an interference in their ability to measure laughing gas accurately. So they asked us if we knew of a way of destroying that methane. We invented something. We had a little quartz tube and we had some UV light, and we were able to destroy all of the methane. And it turned out that was it. That was the idea. And that was our very first prototype, was this little quartz tube, 6 millimeters in diameter. And now we're building things in shipping containers based on that. So that was the beginning.
So a scientist asked you for a favor, basically, is what happened. Yeah. And you're like, yeah, I can do that. And then that's how it just, and then you're like, oh, wait a second. This is just something small now, and I think this is also, where the true innovative step comes in, is like when you looked at it and said, can I do something more with what I just created? And can I scale this to address, other issues? And you wouldn't have had that step if you were already not aware of, the impact that methane was having in the environment, and probably also some of your prior experiences in entrepreneurship as well. So please tell me more about ambient carbon.
Yeah, it's a bit of the right place at the right time. Yeah.
Being prepared, right? I mean, you don't know what you're preparing yourself for, but just keep going and keep learning and keep moving and stay dedicated. And
sure. Well, the earlier story, because you're right, there was an earlier business. And there we were destroying organic molecules, just like air pollution. And we thought if we could destroy it before it got into the atmosphere, then you wouldn't have a lot of air pollution. And the atmosphere washes things out naturally. It makes hydroxyl radicals out of water vapor and sunlight and ozone. And I found a way to increase the concentration of these hydroxyl radicals by a factor of 1,000,000. And so then, pollution, instead of having a lifetime of a month in the atmosphere, it would have the lifetime of a couple of seconds. And that's the amount of time it takes for air to travel through a ventilation duct or a chimney or something like that. So we made like an artificial chimney in a shipping container, and we took it to a factory that was making windmill blades. And we found that we could remove all of the pollution coming from that factory. So that was the beginning of it.
That's a big step. When you say all of the pollution, like it's pretty significant.
Yeah, we were happy. We did a lot
Got
of things
it.
to invent. Yeah, yeah, we got it.
Yeah,
We got it.
got
Yeah.
it. Yeah.
But people were asking me if we couldn't use this invention to get rid of methane. And sadly, we couldn't. Methane is the least reactive of any hydrocarbon in the atmosphere. The carbon-hydrogen bonds are just very resilient, and that's why methane has a 10-year lifetime instead of a 1-month lifetime. And we tried turning it up, and we would put in more UV light, and we would put in more water vapor and more ozone, and we weren't getting any more radicals. And that was because the chemistry had become saturated. And the radicals were reacting with themselves, they were reacting with their precursors, and we were just throwing away energy by dumping in, more light and more ozone. So this little invention from the Niels Bohr Institute, right, when we worked with the Ice Core group, it solved that problem because it was based on chlorine instead of hydroxyl radicals. And this had 3 benefits, and one is it takes a little less energy to make a chlorine atom than a hydroxyl radical. It's a longer wavelength of light, so you win a little bit there. It reacts faster with methane than the hydroxyl radical does. So you get a factor of 16 there. Also kind of fun, but not really a revolution. But these self-limiting reactions are much less severe for the chlorine atoms than for the hydroxyl radicals. And this is because they're atoms. So if they collide with one another and try to recombine, they make a diatomic molecule. And you have the energy of the bond that you just formed within that molecule. It has nowhere to go except to break the bond that it just formed, right? So usually the chlorine atoms, they bounce off one another, and they don't mind having a very high concentration of chlorine atoms. So we can have about 1,000 times higher concentration of chlorine in this reactor than we could have of the hydroxyl in the other reactor. And this intensification of the process means that you can build a small system to treat a lot of air, such as the ventilation air coming out of a barn, or the ventilation air coming out of a coal mine. And so abandoned coal mines, for example, you have to keep the methane from building up to explosive levels. You're venting a lot of methane into the atmosphere. And right now, typically that's just vented, or maybe they use a high temperature thermal catalyst to break it down. But here we would have a room temperature, non-explosive, very low energy, highly efficient method of destroying that methane.
That comes in chimney form, like of various lengths. And so you just be, okay, just go order online and, pick a chimney, pick a process. So,
well, we'll be there in a year, we'll be there in a year.
You'll be there in a year. So that's how far you are now.
When is this going to air?
As soon as possible. So I think we're aiming to air like early October. So anyone that is listening, this is recorded.
So, and that's good news because then I can tell you stuff that's not public information yet.
That would be wonderful.
Yeah.
Oh, I mean, of course, we don't want you to divulge secrets that you're not allowed to, but I think, the audience would be super cool.
We'll have a press release coming out this next week. And so I could tell you things that will be in that press release. Yeah.
So this press release, who is actually having the press release? Like when you say press release, who's giving the press release?
Yeah. So this is Ambient Carbon. And then we're partnering with the Benton Farms in Indiana. And, we're very happy that they have agreed to host the first field prototype of our methane destruction system at their farm. And that's going to be wonderful. It'll be the first field installation of this. We're quite happy to have a solution that works for methane from cows.
That's pretty, that's a huge step. I think people underestimate how hard it is to get your first product out there built, because, this is not something that you're going to find on the grocery store shelf. Like, this is a huge, there's a lot of implementation, execution, a lot of permissions probably that you know need to get into play. A lot of stakeholders involved. So congratulations for that achievement. That's like all the work that people don't see that is required in order to get, you know, science truly out of the laboratory and into the field, literally in this case.
Yeah, it's hardware. You know, it's not software. It's like, you know, you skin your knuckles because you're turning a wrench. That's the level of what we do. Yeah.
So some of the other companies that you have been involved with, because I remember seeing a bit of a list. So can you, and I mean that as a compliment, like this is, and some of them have been, you know, successful, and ambient carbon is, you know, obviously on a trajectory of success, especially with a lot of the new information that has recently come to light with these, you know, unaccounted sources of methane, but also ways to destroy that methane that is somehow very nicely aligned in time, I guess you could say. And so what are the other companies that you have worked on, and what is the status of those companies now?
Yeah. Oh, very exciting. And, you know, thank you for asking about this. So one of the, you know, very interesting projects that we worked on, this is with a company called Airscape, and I'm a co-founder of Airscape. We installed the world's largest network of low-cost pollution sensors in the borough of Camden in London. And so we had 225 sensors all across the borough of Camden. Each one of those had a SIM card, and so it was uploading data every few minutes, and it was loaded with sensors. So we had sensors for airborne particles. We were able to detect those aerosols that we were talking about. Nitrogen dioxide, ozone, temperature, humidity, and carbon dioxide. And this was running, giving us a live map of air pollution in London. And we got just an incredible amount of data. You know, after about 2 years, we had, you know, the most complete data set that had ever been generated of air pollution in a city. And you can spot patterns and things that otherwise have been invisible. Typically, a nation like Denmark, maybe there's a dozen air quality monitoring stations. Of course, a small country, but even 12 doesn't give you very good coverage of all the air pollution. We have one of those monitoring stations on the roof of the building where I work, where my office is. And it's like the Copenhagen urban background air quality station, right? You can go online to the meteorology website and see air pollution levels. But it doesn't tell you the air pollution level, you know, in my office or on the sidewalk or the places where people spend most of their time. And what we've found, because we have these low-cost sensors, is that there can be very large variations in air pollution in cities over very short distances. And I'm sure you've been to Copenhagen, you've seen the lakes, and you know there's a walking path along the side of the lake. There's also a walking path by the road by the lake, right? And they're 7 meters apart. And so our students use these low-cost sensors to look at the pollution difference between the one path and the other path. They had a backpack and a battery in this air pollution monitor. We found that there's twice as much air pollution if you're walking next to the road as if you're walking next to the lake. Twice as much. And you're over the exposure limit if you're walking next to the road. So these hyperlocal variations in air pollution are very, very important in terms of human exposure to pollution. And it's something that we're not characterizing today. And they show excess air pollution over the urban background station that's on the roof of the building and is not next to the street, right? So it's like something that people are not aware of.
I know there's more companies coming, but I think I would really like to ask you about, because when you talk about local, and I just said, you can measure stuff on the roof, and it's almost like you have a stratosphere within a stratosphere. Like you have different layers, right? So I know, you have the different layers that reaches, all the way out to space, and they harbor different types of molecules. But you also have that sort of like another sort of layering that is going on in a city, going on in the country. So, and now you're saying, well, normally we measure on the roof, but when you place these SIM cards with their devices around a city, you actually get a lot of local information. And one of them, I guess you were not surprised that you would find more on the streets where you would get a lot of, cars and stuff driving like that. That's not like okay, we don't need to be rocket scientists to understand that part. But what I do think is quite interesting is that a lot of people are out running, jogging, and some of the information that you provide could actually be very useful for people that are going for a walk. And I just want to emphasize that walking is like one of the best activities that we can do for our health. It's like by far has the most research supporting a healthy lifestyle, longevity, all that stuff. And then there's, some that like to go for a run, which is also very good depending on your age and all of that stuff. But please tell me why local information would be particularly important for people that are going for walking and running activities, because there is something there.
So, Airscape worked on a mapping tool where you would be able to choose a route where you could avoid the air pollution. So that's a very easy application of this information. But air pollution affects us. There are long-term health impacts, but there are also short-term health impacts from exposure to air pollution. So they find air pollution in every organ of the body. And it includes a lot of things. It could be the gas phase molecules. You could have radicals that cause oxidation, oxidative stress in the body. And there are particles, and it could be soot particles or other kinds of aerosols that impact human health. They can cause inflammation and immune suppression and hypertension and cancer. And so the World Health Organization is saying that something like 8 million people die annually due to exposure to air pollution, both indoor and outdoor air pollution. And that's a larger number than are being killed by traffic accidents or HIV, AIDS.
Yeah, and sharks.
And certainly sharks.
And definitely sharks. Yes.
So, as an atmospheric researcher, I think this one thing that we could solve, it doesn't get nearly enough attention because it's loss of life, loss of quality of life, and the immediate impacts.
You also mentioned to me before about how our body has some natural abilities to filter out pollutants, right? So when we breathe through our nose, we go for a run. But you highlighted that when you're breathing heavily, for example, that you may be exposing yourself to more maybe risk, if I say that lightly.
Yeah, sure. Well, one thing is if you're breathing through your mouth, then you bypass your nose, which is a particle filter. And I read a paper once that said, one of our advantages over the Neanderthals is that humans tolerate exposure to things like smoke better than the Neanderthals could. So we could hang out by a smoky campfire, better.
That's interesting.
But even so, we're still impacted by those things. But the way the filter works is, there's air. It's coming at a surface in your nose that's covered with mucus, and you think of the air going at that surface, and then the streamlines of air curve around that surface, and then you've got some particle. It has mass and momentum, and it doesn't follow the streamline. It just crashes into the mucus. And then, I'm very sorry, but humans produce about 1 liter of this stuff every day. And what happens to it You swallow it, right? It goes into your stomach. It gets attacked by, stomach acid and enzymes and all these things, and it breaks down a lot of the pollution. Even if there was something that wasn't broken down, it would still have to cross a membrane in order to get into you. And a lot of it wouldn't do that, and it would just be removed from the body. So you have a pretty effective defense mechanism against inhaling particles. But there's a border to that mechanism. And one of those would be if you're breathing through your mouth, because then you're not using that filter. But another one would be, a heavy particle collides into the surface. But what happens if you have a really tiny particle and it doesn't have that mass, it doesn't have that momentum, and it's not filtered out very effectively? That means that the small aerosol particles actually go into your lungs and they deposit there instead and enter your bloodstream directly. So they bypass the safety mechanism. And something that you breathe could be much more toxic, maybe 10 or 100,000 times more toxic than something that you might eat. And they say that, children eat, I don't know if it's, kilograms of dirt every day, right? And they're just fine. But at least we claim that we're just fine after our childhoods. But something you breathe could be so much more toxic than something that you would ingest. And so that's why we're really worried about air pollution and these things that you could inhale.
What would be examples of some of the tiny aerosols, that the low molecular weight that would have the possibility to diffuse quite readily into the bloodstream via the lungs?
Yeah. So these are what we call ultrafine particles, or PM 2.5, particulate matter with a diameter less than 2.5 microns. That's the aerodynamic diameter. But there could be a lot of sources of these particles. It could be soot made by a diesel vehicle, especially if there's not a filter on that. It could be metallic particles that could come from brake pads and a car or a train, or the wheels of a train on the rails. These all make these very small particles. It also happens that hydrocarbons in the atmosphere, they get oxidized. And those oxidation products, they have a lower vapor pressure. They gather into aerosol particles that forms in situ within the atmosphere, secondary organic aerosol particles. And that's kind of the haze of air pollution that's toxic for people and is killing a lot of people globally.
Right. All right. So this one company that's put out distributed many of these sensors, and you've got now, you said 3 years worth of data. It's a very comprehensive data set. I guess it's also computationally quite heavy to work with that data. How far along is the application of that data set now? Are you guys are you rolling out any sort of modeling solutions that would be able to handle that type of data coming in and to model it?
Yeah, it's a wonderful data set. It's a very unique data set. We combined forces with some very talented researchers at Imperial College in London and published a paper at Science of the Total Environment earlier this year, where we went through that data set. We could find that there were hotspots for air pollution in London, and places where you it's in the danger zone as far as the pollution levels that are seen there. And you could then think of changes in public policy where it might be a low emission zone, or changing the traffic flow from the traffic lights, or changing the mix of vehicles that you have so that you have less polluting vehicles. But it's some kind of information that we need to act based on this.
Yeah, and I think it's far more compelling information too, because if you can use this information to build up the citizen science projects or to activate citizens, they can actually then put the pressure on their local politicians and the government And that's really how you get the change rolling, right? So it's like those regulations are pushed by the people because, and the conduit is the politician. And they need to have things that they understand, but they also need to be aware of things that impact them on a daily basis. And I think this data set could really be a very powerful voice for activating citizens in like, very busy cities. Obviously are going to be the first ones to be affected more. But there's wind, and wind travels, and things settle. This is why we should open our windows all the time to air out our house, because things settle in the corners, and we forget that not opening our windows is also an issue.
My kitchen is a tremendous source of particles, and it could be the stove, it could be the air fryer, the toaster is making all kinds of particles.
I mean, you only have to change your filter, the air filter
yeah.
above your stove to know, like, wow, it's just not grease. Like there's other stuff in there.
The students asked if they could take these sensors and go around Copenhagen into different environments, and they took some of them onto the metro, and they found very high pollution levels on the metro, particle levels that could be in excess of 20 micrograms per cubic meter, relative to maybe 10 that you would have as an average concentration in the most polluted areas of Copenhagen. So very high levels. And you can calculate that if you're taking the metro every day, that would be your main source of exposure to airborne particles. These are mainly from the rails and the wheels and the brakes, and it's metallic particles. So in that case, the students got this research. We made a larger study out of it. And when we published that, the mayor of Copenhagen appointed a commission in order to study the problem and reduce the particle levels. And they've acted now, and they've improved the ventilation, they've cleaned the system, and they've really brought down that pollution. So I'm very thankful for these students who take the initiative to think, what is it in the human environment that could be dangerous to us?
Some of the other companies that you've been working with. So now, we've talked a little bit about ambient carbon, and now we've talked about airscape. I know there's more.
Yeah, there's a new one called Looper.
Looper.
Yeah.
How do you spell that? Luper?
Luper.
Okay.
Yeah.
Yep.
Looper Tech in the Netherlands. They've gone back to that first invention with the hydroxyl radical, and they've found out that it's really good at destroying odor. And so they went to a wastewater pumping station outside of Rotterdam, and you have like a dozen tubes of wastewater that come in, and they've made a lot of gas and some methane and some hydrogen sulfide and things that smell really bad. And so all the residents have been complaining about the smell coming from this pumping station. So they built a prototype, they connected it to the pumping station, and they got excellent removal efficiencies for cleaning that air. So I'm very happy with what they've been able to do in the Netherlands.
Okay, so we have ambient carbon, which is, can basically destroy methane in the air if the setup is there. Then we have airscape, which can help influence, our own navigation behavior, so behavioral change on the ground. And then we have Looper, who is making it more comfortable to live, in areas where you have excessive odors due to whatever processes are going on. So these are three very distinct.
But that's not all.
Oh, there's more. Yeah,
there's more.
It was a list, not the famous 3 bullet points, but a list.
We created a company in Copenhagen called DevLabs.
DevLabs, yep.
And they're developing these low-cost sensors, and we're finding use for these sensors everywhere. And it could be in buildings, helping to reduce the energy use of buildings and improve the indoor air quality. They're making sensors that we tested at the port of Aarhus in Denmark. There they were destroying a building, and they wanted to use green techniques at the building site. And so we were able to measure the amount of noise, the amount of dust and particles coming from the building site, and diesel exhaust. And then they were testing different ways, replacing diesel tractors with electric tractors, or dust suppression systems, or different ways so that the building site would have less of an impact on the city. So there again, I think the information turns out to be very valuable that you can use. They're also developing sensors that we're using at ambient carbon. And these could be sensors that you would put into a barn. We're getting live air quality data from a barn outside of Odense right now. So we see the methane levels, we see the particle levels. We know when they feed the cows because we see the particle levels go up. We can see the cows are producing a lot of carbon dioxide due to all of this food that we're eating. And then you can correlate it with the weather because, when it's windy, you have more ventilation in the barn. So all of this is very valuable for us as we develop our prototype.
So I think some people may be wondering, because I know there's, academics tune in to some of our programs, and like you have 4 companies that are currently active, and I know you had some other companies before that as well. And you're a full-time professor. And I also know that you made a trip down to Washington not that long ago to give advice it was the National Academy of Sciences, which is advisor to Washington, D.C. So, yeah. So, like, where do you find, like, how do you balance this? Or actually, let's not even call it balance, because I'm not a believer that people that achieve things are in balance. I think they are very focused, and I think they're out of balance. And like, you have to lean into something. It's like a runner crossing the finish line. Like, you're not in balance. You just haven't fallen over yet, right? So you're leaning in so much,
Sure.
right? But it's like a slow fall. So and then you do like the arm waving thing as you pass through the finish line. Yeah. So because
I find that innovation has energized what I do at the university, definitely. And I can also see that it gets a lot of traction with the students. And then it turns out, by the nature of things, a lot of these students are then working in the various companies. So for me personally, it's been transformational because you feel like you're really doing something that has an impact. And I was getting frustrated, in the kind of the classical way of thinking about academic work, where we would know everything about air pollution in Los Angeles and in Athens and in London. In indescribable detail, we would know all these things, and nobody was doing anything about it. And so I thought, okay, if I think of myself as having a few skills, I should try to do something about this. And it's helped me a lot. But I'm often working with very abstract theories. And I teach quantum mechanics to our first year students, and you have different reaction rate theories. And for me, at least, having these very immediate practical problems, market problems or climate problems or pollution problems, that motivates really understanding the theoretical things in depth. And it makes it easier to motivate the students. So, I don't want them to study partial differential equations really for their own sake, but because they're so useful in other contexts. Yeah. So it's somehow it all ties together.
I must admit, like, I remember some of my earlier statistics courses in university, and I didn't do well on them, to be honest. But once I got into my PhD work and I actually had a reason to use statistics, like I was seeking answers, then those things become tools. And then you just learn how to, it's a skill, like you learn how to use that tool. It's a very practical thing to lean on. So I think this way of teaching is...
I couldn't agree more. And I think, learning by doing, that's something I encountered in the Scout movement, but it's really true. Or you just look at children. How do they learn language? They don't study, past participles and prepositions and so on. They do. And they're very fast at it too, right? I mean, they just start saying things. Maybe they don't know themselves what it means, but they're doing it, and eventually it takes that meaning, and then eventually, they can see the larger theoretical constructs behind it. But that's the very last stage. So what? Why start there? Let's have the immediate things in front of us and work with that.
Yeah, the why, right, is always about the why. Like, what, like, why should you learn about quantum mechanics, which I actually happen to really like learning about personally. But I think the why, and I think that's mostly because I'm interested in the universe and why we're here and how do we come to be, and maybe a conversation that we can have in a follow-up podcast. What's the meaning of life? so so all of that stuff comes into play.
But but you're also kind of asking, where is the engine, and how do I do these things? And I don't know myself, but I think part of it is that I really enjoy being outside, and I just feel energized by nature. And maybe part of this was growing up in Minnesota, and at that time in northern Minnesota, there was one gravel road between you and the North Pole, right? Because the Trans-Canada Highway wasn't paved at that point, right? So it was true wilderness. And the nighttime sky and seeing the Milky Way and, bald eagles, I would have to go to southern Canada to see bald eagles at that point because of the environmental damage that had occurred with pesticides. But eagles and beavers and bears and moose and all of these things running around. So that's where I go when I need to recharge. It's just, you go outside, you get in the sunlight a little bit, and then I'm ready to go.
Yeah. And it also sounds like you have found some really dedicated students at various levels of education. So, like your bachelor's and master's students. And then I know you have some PhDs as well that you have successfully helped graduate. And then some of those go on to work in, like you said, the startups. And so it's really just a nice flow, but it's also nice to know that the students have access to that innovation path when they go through university. And I think a lot of universities now are starting to look at that more, like, how do we widen that innovation path? How do we make it accessible for students to follow the teachings and the ignition that professors that have been working in the field for many, many years have, they're just sitting on all this knowledge, and, now we're looking to take it out. Do you think that you've changed in the course of your career as a professor? Like, when you first started teaching, and were you always an activist for shaping some of your teachings around, like, understanding how they will impact climate, or did you always push that why out, or was that something that you yourself had a journey, and how did that journey change, if it did?
Yeah, I think I've always been interested in the environment. That's always been true. And maybe part of that is just growing up and being in nature, where you like to observe things and understand them. And you often encounter this idea that somehow science and spirituality are opposite of each other, right? And I don't find that at all. I find that understanding, the reactions that are occurring on the sun, that makes it even more interesting. and thinking about, the distribution of wavelengths of light that are coming from the sun and how that affects the atmospheric chemistry, that adds value for me. So I don't see these things, as opposites, but rather as complementary, definitely.
Yeah, it's just understanding the world, right, and how to make it better. And again, looking at these things as, solutions to puzzles, tool sets, all of that. And of course, learning is a very enjoyable process for many, and many of us have different forms of learning, and some types of knowledge is done in certain formats of learning. But now we see a lot of, growth and online education, videos, people that are taking the time to make it both visual but also audio. And then you have books, which is the the studying. So
Yeah, that's true. I did a lot of online teaching during the pandemic.
yeah,
I like personal interaction.
I miss
I
it.
think you need to see people. Uh, you were talking about the students. This is the greatest resource that we have, and I get so much information from the students, and not information, but information too, but inspiration from the students. And I don't think they realize the power that they have in asking questions and just in being there. And, maybe a student says, oh, I'm interested in, doing something with agriculture. And then that helps me so much because there's a person that I can tie that project with. And I think, I have to send them this article and I have to send them this article. And I need them, that entire team, to get the things done. If I sat in a room by myself, I wouldn't get anything done because I need to help people, right? And I think, okay, I need to finish this for Olga, I need to finish this for Louisa, and I need to do this for Martin. And it's not really it is the science that I'm working on, but it's the human contact. So I find science it's a very human enterprise, right? It's human culture that we're doing. And it's words that we're creating. And it's kind of a process of magic where at one point you're like, we could use chlorine to do that. And it's just a crazy idea. And you think you're nuts. And then somehow you develop the words and the language and the concepts. And before you know it, you've got an agreement with one of the largest dairy operations in North America, and you're putting your prototype into the field in the first quarter of 2025. That's some kind of witchcraft that you can go from ideas to actions in the real world. That's the fascination for me.
Do you have any advice for other, scientists / entrepreneurs that are working at that boundary? So the ones that are interested in translating their science out, because getting those contacts can feel really far and out of reach for some people that maybe don't have the network. It sounds to me like you have established a network over the many, many years. Is that the advice? Like, work on your network as a scientist?
Okay, so I think one piece of advice that I have is this is something we say in thermodynamics. If you have a piston, the internal pressure must exceed the external pressure in order for useful work to be done. You have to have that internal pressure in order to go out into the world and do things. And, I think there's a risk that people see one other success and they think they have to emulate that success. And so everybody wants to be Steve Jobs or Bill Gates or, whoever it might be. But that was them. That was their story. You have to make your own. And I think it's a very useful analogy to artists who just have an empty palette in front of them, and they have to create something out of nothing. That's the magic of the mind, is to create something out of nothing. It's not because you copied somebody else. Maybe you were inspired by somebody else, certainly inspired, and you need some skills. But that creativity, bringing something new into the world, that's the magic part of it. And that's something that you have to bring it out of your own experience and will and so on. So a lot of people can understand accounting, I think, and the laws of business and so on. But bringing something new into the world, that's the key. That's the hard part, I think.
You're saying that they need to recognize that is the beautiful part of...
That's the beautiful part.
Bringing something out of their scientific work, that internal pressure. Do you think that people don't have a way to build up their internal pressure? Or do you think it's fear that maybe is holding a lot of academics back? Because I have met a whole spectrum of academics, and some are like very, very happy to focus on fundamental research and very basic theoretical work. And
Which is great.
this is
Yeah.
great. I
Yeah.
mean, you need that. I mean, otherwise, we wouldn't have things like statistics and quantum mechanics and whatnot. So eventually they find their way into the world. But I would say like a large majority are working in applied sciences, and even sociology, which is also a form of applied science. So what do you suppose is holding them back? Like how could we build up their internal pressure? Because I think that we need to activate more scientists to pursue ways to make sure that the science, like the work that they have done, actually like crosses that chasm, like becomes the magic that you spoke of. Any advice for someone that is maybe a little bit timid?
Yeah, that's a great question. And I don't know if I can give because it's such a great question, it demands an excellent answer. And I don't know if I can give an answer that's good
You
enough,
can try.
but I can try. I can try.
You can
So,
try.
there's a risk that you're working to please the teacher. And I think that for many people who go into academics, school was the place where you could get some recognition and do well. And so that urge fights against this thing of creating something unique yourself, because you think you want to do something that will be accepted by them. And of course you would like your work to be accepted and seen well, but in finding your own voice, that's the key, right? Because you're not somebody else. You shouldn't try to do the same work that somebody else would do. You need to find your own voice, your own unique contribution to the world. That's what I would say.
Yeah, and then broadcast that voice to the world. And I think that's where we're seeing a little bit of the chasm, right? This idea that we have our echo chambers within our scientific communities, and it's okay to be, like in dialogue with people that have the same deep knowledge with you, because this is a way for you to articulate and test your knowledge. But at the same time, we need you to, like, people to cross that boundary. And
no, it's true. But there's always both good and bad aspects to everything. And little community can be very useful sometimes. It could give you a lot of energy, and you do need trusted people that you can discuss different things with. And often you form your own little language. And I think that in academics, that can often limit communication between, because we love acronyms, and there's TLAs flying around everywhere, 3-letter acronyms. It can be good and bad, right? And I think sometimes it can be a defensive mechanism where you don't want people to understand what you're doing, or you want to make it sound more complicated than it is, because you think I'm not good enough, right? And so then I felt very challenged when I read something. I think it was Feynman who said that, if you can't explain it in a simple way, you don't understand it. Einstein said some things like this.
yeah, he said something to the same effect.
Make everything as simple as possible, but no simpler.
Yeah. So I think I 100% agree. I find that so I've worked in scientific communication for it was a passion project of mine that started at the university, in my transition from PhD to postdoc. And I found that, or I acknowledge that, especially as a young academic, that you're so worried that people will not think that you're smart enough. And it's probably like the hugest fear. And so when I started to change my teaching style and my presentation style to be ultra simplistic, it's like working against a reflex. And you had to accept the fact that it was going to appear simple. And maybe some people would walk away from your presentation and think, well, that's so simple. And you're worried that if they think it's simple, then suddenly, like, you're simple, like you're just a simpleton. And no academic wants to be cast in that light, right? So I think it was about really like overcoming that reflex of knowing that, yeah, like if you can make things understandable for your audience, and if you can simplify it for them so that they walk away with an understanding, they won't actually think that you're a simpleton. They'll actually love you for it because you taught them something. And I think sometimes we forget that. So it's like the fear is presenting, a barrier for many of us, because we, our reputation is at stake, and we're supposed to be working on really like complicated stuff. So like if you go up and give a presentation, it sounds so simple, then suddenly that lack of complication means that you're not a qualified researcher anymore. And it really is a point of friction. So I 100% agree. Like we hear the sayings like, can you just make it simpler? And people are like, well, no, but yes, yes, you can.
You can't make it simpler,
No, you can't.
It really
right?
is complicated.
But you can explain it so that it's understandable, and you can explain it simply, even though it's a very, complicated process. So yeah, I think this is also like the fear of being viewed as not working on something that is hard. I think that is excellent. Is there like we've covered a lot in this podcast, and like Matthew, is there any questions that you think that I should have asked that I didn't ask, that I maybe glossed over in our discussion, especially about what's going on with methane, its current status? Do you think actually I just reminded myself of something. Do you think now that the research that you have produced has the potential to really engage like politics more? Like you mentioned that some of the data sets that you got from like mapping out London, that had a very, like how long, for example, that lifetime took, like 2-3 years for you guys to start activating, political stakeholders. Where do you see this in the case of methane and the project that you have worked on recently?
Yeah, very, very good question. The National Academy of Science in the United States is coming out with a major report on Wednesday next week.
Wednesday, October 2nd. Yes.
And I think that when people think about climate change, the general public, they think about carbon dioxide, and they haven't been thinking about methane. And so, the dream, the hope, the ambition is that this report is going to put methane into the public consciousness in a way that it hasn't been before. And the narrative is a bit different because with carbon dioxide, it's fossil fuel. And sometimes people have, approached this as a us versus them, or a good guy and bad guy, because you have fossil fuel producers who are actively lobbying against the very belief in climate change because it affects their bottom line with carbon dioxide. So the narrative is more complicated with methane. It's related to food and human activity. And then it's a bit more about ourselves and maybe the food that we eat. And one thing that I hope is that by decarbonizing the food supply, we won't have that concern anymore, right? So you can have meat and dairy, and it'll be a low carbon product. That's where I would like to go. But you ask about what we could have talked about that we didn't talk about.
Yeah, I feel like maybe I missed a few steps in our conversation, so this would be the time.
Well, I feel rather hopeful about the progress that we've made as a society, especially as regards our energy supply. North Dakota, of all states, was exporting green energy, and they had over 100% of their energy from renewable sources during a 12-month period. I think that's wonderful. I wouldn't have expected it, but we're there today. Norway is also exporting clean energy. So, there are examples that show that it does work. that even though we have problems with, I don't know what the objections are, that windmills are ugly and, all of the things you hear against renewable energy, or that the sun doesn't shine at night, or the wind doesn't always bright. You can balance it. You
It's
can find
shining somewhere.
solutions. It's shining somewhere, and it actually works. And I think it's a case where, in some way, we're vested in the infrastructure of the past, where you build a coal-fired power plant, and then you're committed to using it for the next 30 years. But the United Kingdom, they were first in the world to build a coal-fired power plant in, I don't know, 1840. It was a very long time ago, 140 years ago. They're now going to be the first in the world to shut down all of their coal-fired power plants, and that it's being decommissioned right now. So they're led the way in one respect, but they're also leading the way in another respect. And you can find a lot of these stories that show that we are making this transition, and it's actually a benefit. It's not a sacrifice to be making this transition.
Right. So to just summarize that, so there is actually a lot to be hopeful for. There is a lot of progress that is happening, and probably because it's such positive news, it gets less media attention. Again, this is how we're built. So there's so much to be hopeful for. So maybe when this news, breaks about methane, where now we have to say, really look at ourselves as individual contributors to some of the major problems that are, literally at our doorstep. That maybe we are now having the capacity to really embrace that rather than feeling defensive. Maybe we can take the offensive. And you believe that our society is at that critical junction now, that there's enough awareness that people won't go on the defensive. Because I've talked to some people, and they're they have some great products, some that can facilitate transport, so getting less cars and trucks off the road, putting that stuff onto trains, and they'll say to me well, Shelley, the consumer wants what the consumer wants. And so you have these companies that have, delivering us all these products and services. But if the consumer doesn't want and doesn't demand, to see the supply chain, to see that it's green, then it's not cost effective for the companies to do that. And so they're just responding to consumer demand. And, and it's really hard for them because most people just look at them as money hungry individuals. They're not. They're just responding to the market.
Yeah. I think it's important with a diversity of points of view and perspectives on the problem. And that's not the only perspective. And I read a very interesting article in The Economist about farmers who were growing poppies in Afghanistan. They need to irrigate, right? So they pump water in order to irrigate their fields. And, they have diesel-powered generators that run these pumps. And satellites were showing they've all gone over to solar power. They don't do it for the environment because they're worried about the diesel emissions. It's actually cheaper. So I think a lot of times we're able to leapfrog because of this innovative process, because somebody found a better way to do things. And then it's not an issue anymore. It's not an either or thing. It's that we can leapfrog it and we can go beyond it. So I would say let's transcend these problems, and there is the potential for doing that.
Yeah, but a lot of the reasons why it is economically viable and beneficial, as you pointed out, is because there's been a massive investment in the innovation. So a massive investment in innovation funds to actually get us to that point that they are economically viable. So
it seems like Moore's law applies to solar panels, and the price per watt of generated electricity, it's gone down orders of magnitude during my life.
Yeah, and it will continue to go down from what I understand. Yeah. And then now it's all about storage and how to harvest that. For example, when the sun is not shining or the wind is not blowing.
investment is usually, in this case, it's not a sunk cost, right? I mean, we're enjoying the benefit of that past investment right now because we have renewable energy.
All right. So, Matthew, thank you so much for joining me on Bonded by Science. And there's just so much information. This is just a packed full podcast of golden nuggets. I wish you the best personally in your endeavors, but also the most success to the companies that you have helped initiate and the students that are participating in those companies. They sound so very promising. I cannot wait to follow more of what you're doing and have you back again, potentially maybe with some of your students. I would really, really love to interview them as well. So thank you, Matthew, for your time today, and such a pleasure meeting you.
Really a pleasure. Thank you so much. Thank you.